Here's all the material we need for the dehydration of cyclohexanol. We're going to need 10 milliliters of cyclohexanol, 3 milliliters of 85% phosphoric acid. We're going to need a small amount of 10% sodium carbonate, some distilled water, some anhydrous calcium chloride. I like the beads that are easy to pour out. For the separatory funnel and extraction portion of the lab, you'll need a couple of small flasks, a large 250 milliliter Erlenmeyer flask, and a funnel. This is a 125 milliliter funnel, and ideally you should use a ring stand that fits, and a ring, and maybe a dropper to transfer the pure product. Now for the reaction itself, we're going to use a simple distillation apparatus. So I've got those items here. I've got my steel pot, my steel head, the thermometer adapter with thermometer, a clamp to hold the steel pot, and I use these plastic joint clips here to affix the joints together. Okay. Now we will be receiving the product in this small flask here, and we're going to keep it cool by placing this in the ice bath. Okay, so let's go ahead and swivel the camera around to the fume hood and get that set up. All right, here we are in a trusty fume hood. So start off by putting your ring stand in here. Put the hot plate on top of the ring stand. I position this somewhat close to a faucet so that the water lines can reach your water line. I verified this both stirs and heats. Now, in the round bottom flask, we want to place 10 milliliters of cyclohexanol. I'm using reagent grade cyclohexanol, and the information here on the back of the bottle can be very useful in terms of calculating theoretical yield for your chemical reaction. The cyclohexanol is the limiting reactant. So we want to place 10 milliliters into this 50 milliliter round bottom flask. And these little cork rings are great for holding the flask so they don't roll around the tabletop. I don't know why they're so expensive though. So we'll go ahead and measure out 10 milliliters of this using a plastic pipette. It's the best way to conserve reagents. We don't want to pour 200 milliliters of this into a beaker and then get our 10, and then what do we do with the rest of that? We're not supposed to return reagents back to the bottle they came from, so this is usually the best way to measure out a good 10 milliliters. And you might just have a few drops of waste. Okay, and I'll put this back in the waste over here. All right, so we've got our 10 milliliters cyclohexanol. We add that in here. And it's somewhat viscous. I like to wait a few seconds for the cyclohexanol to fully come out. But as you know, some of that is left behind, and there's some inefficiencies always in the synthesis. Now we want to add 3 milliliters of phosphoric acid. Phosphoric acid is very viscous, extremely viscous, like, not quite like honey, but extremely viscous. So I'm going to use these markings on my pipette to dispense 3 milliliters of 85% phosphoric acid. This is just a catalyst, but we really go overboard here and we use a lot. Okay, so there's 3 milliliters. Okay. All right. So that's been added. As I mentioned before, phosphoric acid is the reagent in excess. I'm using the ACS grade, 85% phosphoric acid, and some of the information here is on the bottle: the molar mass, the percent, some of the impurities. Okay. All right. I'm going to now clamp this. And everything rests on this, so we want to make sure that it's very centered and good here. Now I'm going to get a stir bar and place that in there. These stir bars are great because there's a little magnet in here and it's coated with Teflon, so it looks white, and that white plastic is quite inert. And if that's placed in here, we can use the stir plate to cause that to stir automatically. And all that's underneath here is a spinning magnet. Okay, it's a motor hooked up to a spinning magnet, and that will spin all by itself. So it's great. It's a lazy invention that chemists invented many years back. All right, now we need to assemble the rest of this distillation apparatus. So to do that, we grab our still head, snap that on here, and I'm going to angle it this way away from the water. The next thing we do is we insert a thermometer into our thermometer adapter, okay? And when you do this, you want to make sure that your thermometer is located about there, okay? So the top of the alcohol or mercury, if you're using mercury, is level or lined up with the bottom of the neck, okay? So when the vapors come up during distillation, they should pass over that bulb and go into the sidearm there, okay? I've got this a little low, okay? But something like that would be a good alignment for a distillation, okay? So you can put that in there now, okay? And as I mentioned, I use these joint clips here. They're sometimes called Keck clips, and they're used to affix the jointed glassware together. And so we'll put this guy on the sidearm here. All right, and that's a very sturdy clip there, okay? And so as long as your clamp's good, it should be fairly secure, okay? Now, we always want the water to go in the lowest part of the jacketed condenser and come out the top. So we'll hook this up, and like I said, this has to reach all the way over to the faucet here, okay? It's a good idea not to have your rubber hoses touching the hot plate. They might melt. So I try to get them situated over the clamps, things like that, so that they're not in the way of things. At this stage, it's okay to move this a little bit closer to the sink as well. Now we'll turn on the water now just to get a good idea of the flow. Make sure the plumbing's on, everything's good. And you can see the water starting to fill up the condenser, possibly on the camera. And you just want a low little flow of water there, okay? So that there can be directed down the drain. Okay. So now that we know water is flowing, we can assemble the rest of the apparatus. So we can begin heating this up. So I'll start the stirrer here, and we'll set this up on a setting here that's pretty high to get this going quick. All right. Right now, room temperature here today is 22.8 degrees Celsius. So to get this ice bath set up, I like to put a little water in there, and we'll put this flask underneath it to collect. Okay. Now you might have everything set up perfectly to your liking, and then to your horror, you might discover that the ice melts and then your flask shifts around. So you need to really be careful of this. My line seems to be leaking, so let me fix that. Okay, now it's just a waiting game. We wait for this to heat up to boiling, and for the isotropic mixture of cyclohexane and water to come out and come into our flask there. So I'll fast forward through this part of the video and come back, and you can see what it looks like when it's starting to boil. So as you can see behind me, the solution is now turning a very dark kind of yellow and eventually orange and brown. If you really start trying to heat this, the temperature is about 92 degrees right now, and there's no more distillate collecting in the flask. So I think what's left in the flask is you know, a whole bunch of stuff probably, but phosphoric acid mainly. Those 3 milliliters of phosphoric acid, 85% is phosphoric acid. The water has mostly come out by now, and so we can shut this down. I'll keep it stirring to dissipate the heat, but I'll turn the heater off, and that's about it. Now if we take a look at the flask, and by the way, I'm not running this fume hood, so I won't overwhelm the camera with noise, but it really does smell like an alkene. You just have to smell it the first time to really understand what it smells like, and then you'll know what that means. But in my ice chilled receiver flask, this is really has a strong smell. It's a cloudy solution right now. But it's a suspension of insoluble cyclohexane and water. So that's it. It's about, you know, looks like about 10 milliliters of total volume of water and organic materials. So now we do the extraction. And we'll do that right here. So what we'll need is a separatory funnel. And if you're doing this lab in person, you really want to make sure that you close this valve, because if you don't and you pour this in, you'll lose it on the ground and you'll have to restart the experiment. And chances are your lab instructor won't give you more time to work on this because it's a 2.5 hour lab. All right, so we're just gonna add this in there. And the nice thing about separatory funnels is that you can actually see the layers a lot better than in a flask. So the bottom layer, remember, is going to be your water, and the top layer is organic. So that's great. That's huge. We got a lot of product there. So the procedure calls for washing with sodium carbonate. I'm going to get that. And I believe this cap is fused or stuck. Nope, it's not. All right. So I think 10 milliliters is what we want to use here. Or maybe it's 20, I don't remember. I just use this as a simple kind of way to measure. Okay. So that's about 15. It's below the 20 mark. We'll go ahead and add that in there. Now the purpose of sodium carbonate, since it's a base, is to remove any residual acid that may have snuck in through the condenser into the flask. I didn't see it bubble at all. It's not bubbling now, so I'm pretty sure there's no acid in there. But this is just a precaution step, because remember, if you react an alkene with water in the presence of an acid, you can form an alcohol, and we don't want that to occur. So remember again how to use the separatory funnel. You hold the cap always, okay? Vent. And I'm not gonna do that so vigorously and strong, but now we wait for the layers to separate. It looks like salad dressing right now, so we need to wait for the layers to separate. So that looks pretty good. This step is called the washing step, and with washing laundry, for example, you want to discard the dirty wash, right, and keep your clothing. So the stuff we want to keep is the top layer, which is the organic, which is less dense than water, and the stuff we don't want is in the bottom. So I've just got this large flask here that I'll use for discarding the washes. So we'll go ahead and put that in there. Again, this stuff just smells ripe. Now, this is not the last step, so it's okay if I leave a little bit of, you can barely see the layer there, a little bit of water there, a little bit of aqueous phase in there. Now, the step we do now is to add a small amount of water, about 10 milliliters. And the purpose of that is probably just to remove any residual sodium carbonate. So I'm using distilled water. And this doesn't need to be measured super accurately. Generally, you want to wash with an equal volume. So I'm going to add about 10 milliliters. Of water in there, so that's about 10 milliliters. And this would be like when you do laundry, you do a rinse cycle just to remove any kind of extra soap that's in the laundry, right? So this is the rinse cycle basically, but we still call it washing. Okay, so we want to wash the organic layer here with 10 milliliters of water. Always be sure to vent away from your face and your lab partners. And a minute of vigorous shaking is all you really need. We'll wait for the layers to separate here. And And this will be the very last separation. So now I can put this stopper on the countertop. I'm not worried about contamination. The layers seem to separate very quickly. As it gets more pure, things separate more quickly. So now what we do is we transfer this to the waste again. This will be my last kind of washing step, so I want to make sure that all the aqueous is removed as much as possible. Okay. And now you're never going to get all the water out. Why is that? Because there's water droplets on the outside of this. You might have a tad bit on the bottom of this layer, and then also remember that the valve has a hole in it, right, for it to flow through, and it's filled with water right now, and there might be 1 or 2 drops of water in the separatory funnel as well. So that's why we dry organic phases. So what I'll do is I'll put this over a 50 milliliter Erlenmeyer flask, and I'll just let it go out. Okay. This is maybe a bigger flask would have been better. Okay. And we'll spill it there. All right, so you know, that's as most as we can get in there. And now the procedure calls for adding a small amount of calcium chloride. Now this is anhydrous, and the purpose of adding this is to absorb any water that's in there. And if you look at the flask, I'm not sure if you can see this on the camera, but you can see a little droplet on the bottom right there where I'm pointing to. Okay, see that wiggling around in there? So the calcium chloride, since it's heavier than the organic layer, it'll sink to the bottom. So a scoop like this is kind of all you need. Okay. And water also sinks to the bottom, right? So water is on the bottom of the organic, and so is the calcium chloride, which is great because the calcium chloride has to interact with that. You can also kind of jiggle around the sides there to get the water. Now, if your calcium chloride all clumps up like mine is, you know that it's probably going to need a little bit more calcium chloride. The best way to do this is with magnesium sulfate or sodium sulfate, but these very fine powders require filtration. And that's just one more step that you have to do. So sometimes I like to use these large beads of calcium chloride because of the surface area isn't as great. They're less efficient in drawing, but it's a lot easier just to pull your product out. We can just put in a little pipette and withdraw it, and then we have our product, okay? Now what we're looking for is a free-flowing solid in there, and then we're also looking for a crystal clear solution, okay? There shouldn't be any water droplets in there that you can see or make out, okay? And I like to kind of jiggle the liquid onto the sides of the flask just to interact with any maybe water that's up on the sides, okay? And it takes some time to do its work, so it might look crystal clear, but water will have a finite solubility in cyclohexane. So if in your lab you're doing infrared analysis, you really want to make sure this sits for a good 5 minutes or so before you do your analysis, okay? For me, I'm just going to do a Bayer test today, so I'm going to go ahead and transfer this, okay? Now we want to weigh this product now, so I'm going to grab a empty, clean, dry 50 milliliter Erlenmeyer flask that looks just like this one. I'm going to weigh it, and then I'm going to transfer the product in there, and then weigh it right after that, and then I'll be able to calculate the, my students will be able to calculate the yield, all right? So let's go ahead and do that. Here's my balance. I'll make sure it's zeroed. Let's take a look at the numbers. So there's my balance that's nicely zeroed out. And here's the clean, dry flask that I mentioned. Okay, there's the mass there. Okay. And then what I will do is now when you transfer the liquid, it drips out really quickly. So what you got to do, a good trick, is to hold the two flasks like this, so the neck of this one is very near the neck of that one. And also, of course, wear gloves to prevent spilling this on your hands. But this is COVID, and all my gloves are at my house. Okay. So just aspirate that in like so. Okay. And then move it over and dispense. Okay. And if you do that carefully, it shouldn't drip in between, and it should all go where you need it to go. So that's quite a bit of product there. We got two big old squirts. Okay. And that's kind of what it looks like there in the bottom of the calcium chloride. It looks damp or wet from organic material, but what can we do about that? All right. So there's the calcium chloride that's left over. Okay. This smells really bad, so probably you want to dispose of it in a fume hood in the solid waste container. All right, and here's my clean, dry material. So it's nice, sparkly clear, okay? That's what it should look like. You want to keep a cork on this when you're not using it, because it will evaporate and it smells. So let's put this on the balance and measure its mass. All right, so my balance is zeroed out. And there we go, we've got our mass, okay? So this should be cyclohexane now. And I'll pause the video and we will do the Bayer test with the potassium permanganate. All right, let's do the Bayer test. Most things in organic chemistry, if they're right, they should be white, clear, colorless, you know, crystalline. This is one of the few things that has color. So potassium permanganate is a nice purplish color. And here's my alkene. So this is about 1 milliliter of solution, and we're going to observe what happens when 1 drop of this is added. I added the 1 drop and nothing happened, right? So we gotta mix this up. Best way to do that is jam on your guitar here a little bit. Boy, does this smell. Cap this here. All right. And now we want to make the observation there of what that looks like. Okay. So go ahead and make your observation. The lighting isn't too good right here right now, but hopefully you can see it in front of the lab coat there, okay? All right, so that concludes this experiment. I hope you enjoyed watching me synthesize cyclohexene from cyclohexanol. This reaction proceeds by an E1 reaction mechanism, and that's the product. Well, that's the product. And so we just dihydroxylated that alkene with potassium permanganate. There's many reactions that alkenes can undergo, and I hope you find organic chemistry as interesting as I do.